Good morning and welcome. Thank you for coming to SDC. And thank you for coming to hear about what's going on with key value storage in the standards arena, both at SNIA as well as at NVMe. I am Bill Martin. I am from Samsung. I also happen to be the co-chair of the SNIA Technical Council and representative on various standards committees. But I'm here today to present predominantly from an industry standards point of view on the standardization efforts that are underway for key value interfaces. I do have to, as a member of Samsung, provide a disclaimer that nothing I say can be held against me or my company. So with that said, we will move on to what is key value. Key value is a mechanism that is different from your traditional block storage paradigm where you store user data associated with a key. That key can be anything you want it to be. It could be a URL, it could be simply a name, it can be anything you want it to be. The key may be any length. It is a byte granularity. The value, which is your user data, may be of any length. It is also a byte granularity. Now, with a caveat here, that's the concept, not necessarily the practice in terms of length. So this is a definition, but it's not the definition of what's being standardized today, and we'll talk about a little bit more what we're standardizing, where we see ourselves going in the future, and how we plan to get there. So what are the differences between KV and block interfaces? Well, in the block interface, most of you are probably very familiar with block interface since you are storage developers. But user data is in multiples of a block length. The block length will be different on different devices, but nonetheless, it's in multiples of that block length. Logical block address is a number from 0 to a maximum logical block address on your device. Now, various devices may have thin provisioning where you don't have enough storage for all your logical block addresses, but nonetheless, you're limited to a logical block address that fits within some fixed space. With key value, you have variable length user data. That can be 1 byte in theory. Storing 1 byte may not be the best thing to be doing, but in theory it could be a byte, it can be a megabyte. There is no definition of it in terms of blocks, it's simply defined in terms of bytes, how many bytes you have. The key, which addresses your data, is also variable length, and it is an identifier. And so instead of being stuck to a logical block address that is of some fixed size, you have a key. Now, it doesn't mean that if you took a key that is 16 bytes long and went and started at the number 0 and went to the number all F's for that 16 bytes, that there is storage for all of those keys. So it is inherently a thinly provisioned device where you have a lot more potential keys that you could define than what you can actually store on the device. So, differences between object and KV interface. This is a little bit more subtle. There's been lots of things out there about object interfaces, and why are we doing something that isn't an object interface? Well, KV is a tool to facilitate object storage, but it's not a full-scale object storage. In particular, keys are not required to be ordered or be able to be retrieved in an ordered fashion. In other words, if you took and did some alphanumeric ordering of your keys and wanted to find all of your keys, key value doesn't provide for you to do that in some alphanumeric order. It will give them to you in a repeatable order as long as you haven't stored something new or erased something from the device. So if there's no change in state, they will always come back in the same order, but there's no requirement for being able to retrieve your keys with some fixed alphanumeric ordering scheme. It's also not searchable based on the contents of the value. So I can't say to my key value device from an upper layer, go find me all of the key value pairs that have this particular social security number in them. It's not intended for that level of object storage or object searching. So with object storage, the keys can be requested in some form of order. There is more functionality to search the objects. In other words, you can ask your object storage for something that has a given value within it. It also, one of the other key factors that's a difference between key value and object storage is object storage generally supports logging or other mechanisms to maintain your database integrity. Key value is an underlying technology to help support object storage, but the logging to make certain that things are there, to make certain that there is database integrity, not data integrity per se, but that if you stored a whole bunch of things that you are consistent in the event of a power failure, those types of mechanisms are in the software above key value that actually runs your object database. Now, that doesn't mean that you don't have some level of atomicity. You do, with what we're defining, have atomicity of the key value pair. So an individual key value pair, if you store it and you get a power fail in the middle of it, you either get all your old data or you get all your new data. But there's no logging to come back and tell what have you or what haven't you done, or a replay mechanism. So what are the layers of the key value SSD system? So you've got the application layer. That application layer is talking to a key value API. And we'll talk a lot more about that because the example here is the SNIA Key Value API, which is half of what this talk is about. Then there is a library that talks to a key value protocol host interface, and then that talks across a key value wire protocol. The example I've shown up here is an NVMe KV command set. Again, that's the other half of the talk. That's where we'll spend the other half of our time. And then at the bottom end, you have a key value SSD, or a key value device. I put SSD because I work for an SSD company. I don't work for a spinning Rust company. You could have a key value piece of spinning Rust. So again, that's an example, but basically you have a device that understands the key value wire protocol and can store things appropriately. So first I'm going to talk about the SNIA KV API status. Or the first half of this talk is going to talk about the KV API. So the status of it is that it has been, version 1.0 has been approved. It is publicly available. It's got a website there that you can get it out off of SNIA. In addition to that, there is open source code available on GitHub at that particular location, which the slides are available online for you. All of this is there so you can easily get at those links. It allows library calls independent of the underlying transport. So what that means is if I'm talking key value over NVMe, or key value over SCSI, or heaven forbid key value over SATA, all of those, the API will be the same for all of those. So what does the API define? First, I want to talk about structure. So it has a multi-level structure. It has a key space, which is equivalent of a namespace in NVMe, but it is a space for which, in that entire space, your keys are unique. So if I have two different key spaces, and I have the same key, they have different values potentially attached to them. They are not unique across multiple key spaces. So there is a uniqueness there of your keys within a particular key space. There is a key group. The key group is unique within a key space. It is a group of key value pairs, and those key value pairs are enumerated by some portion of your key and a mask associated with that portion of the key. So you could say all keys that have this group of bits set to some value would be a key group. So that is a structure that allows you to identify a group of keys within a key space. The key value pair is the fundamental building block that we are talking about, which is a key associated with a value. In addition to that, the API defines a structure about device information, which is characteristics of the entire device, which includes all of your key spaces. So this would be, how much storage do you have for all key spaces? How many key spaces do you support? What is, from a device point of view, what's your maximum key size? What's your key granularity? What are your optimum value sizes so that you can attempt to store things optimally on the device? What is your value granularity? And the value granularity is an interesting characteristic in the fact that when you are storing a key value pair, you may have a value granularity that is, say, 2 KB. If I attempt to store a value that is 1.5 K, I may actually utilize 2 K worth of my resources because I don't want to fragment my physical back-end storage to accommodate these little chunks. Part of what this does is this actually avoids some of the write amplification on an SSD of the fact that you're not trying to do a lot of garbage collection. When you store a key value pair, if you work within that optimal granularity, then when I'm ready to delete it and write something else, it's a single chunk or multiple individual chunks of my memory space, so I delete them completely, and I don't have to do garbage collection to say, oh, in this physical area, I have part of this key and part of some other key that are both in that one physical area. If you follow the optimal granularity sizes, then you don't have that issue. And then there's key space info, which is the characteristics of a specific key space. And that will have your information about how large is your key space, how many keys are currently allocated within that key space, how much storage do you have available, etc. So that would be specific to a key space that you have created within the device. So then what does the API define in terms of access? It defines a store operation, which is fairly simple. You store a key value pair. It defines a retrieve operation where you retrieve a key value pair based on a key that you give to it. It defines a delete operation to delete a single key. It defines a delete group operation, which goes back to the concept that I mentioned earlier of key groups, where a key group is keys that are defined by some portion of the key matching some particular pattern. and it allows you to delete all the key value pairs in that key group. It has an exist function to say, I want to query the device and ask, does this particular key exist in the device? The exist function is written in a way that you could actually pass it an array of keys. So you may ask if a whole set of keys happen to exist, and you get a response that indicates on a per key basis whether those exist. It provides a list function. That list function follows the rules that I said earlier in the fact that your list will be consistent from one call to another, assuming you have not done any store or delete operations in between the two, but it will not be in any sort of, it is not required to be in any sort of alphanumeric ordering. Now, one of the things about the list operation is it needs to be consistent from one time to the next, because if I cannot buffer all of the keys when I do a list, I need to have a mechanism to go out and ask for more keys. And so there is a parameter passed in which is a key. So if I do a list of keys and I pass in all zeros, so I say start at the beginning of whatever your list looks like, whatever the data structure you store is, I return a set of keys that fill up whatever buffer I've allocated for that. If I then take and do another list, starting by asking for the last key that I retrieved in the previous list, it will continue on from there and give me the rest of what's out there. And that way I can walk through and get a list of everything independent of whatever buffer size I'm transferring in. Then there's an iterator, and move into what the iterator function does. So the iterator function is a mechanism to enable a device to prepare a key group of keys for iteration by matching a given bit pattern. So what this does is, if I know what my key group is, this function actually allows me to go down to the device and say, by the way, here's the key group that I want to have. It allows the device to then say, oh, so that's your key group. I need to create data structures to support that key group. So I need to go through, if I've already done a whole bunch of stores, then I need to go through and figure out what all of the things you've stored on the media happen to fall into that key group. So when you want to do something with it, I'm not going and trying to walk my list to find all of those pieces of key value data that happen to match that particular key group. So it's a preparatory mechanism for the device to prepare the data for whatever you're doing with the key group. It also is a mechanism to go out to the device and say, as you do future stores, you need to be aware of key groups and be able to continue to update your data structures that are going to come down later and reference those key groups. So the iterator function is something that first off allows you to prepare the device, and then it allows you to list or delete key value pairs within that key group. So the iterator function is what allows you to then say, okay, I want to list my keys, but I only want to list the keys that fall within this particular key group. Or I want to delete all of the keys in this key group.
Is there a guarantee of any ordering within that key group?
No. The same ordering requirements that I already specified. There's no ordering requirements, but if you look at that 2 times in a row without doing an intervening store or delete, then it will be consistent. Now, a device could be built that gave you ordering, okay? But that's not a requirement of the API. So Now I'd like to move, so that's the extent of what we have done currently in the key value API. The one other thing I want to throw in as one final caveat on this that maybe belonged at the beginning is there are a couple of things that as we have gotten further along the development path we've found are going to need some enhancements or improvements. In particular, the key value API allows for asynchronous commands. We're missing a couple of parameters that need to be passed for that, so there will be an update to the key value API. However, I don't expect that to come out until after we get fairly well completed with the NVMe key value command set. Okay, and at the end I'll talk about schedules related to that. But so we have a version out of the API. There are some things that are known already that need to be put into a next version of it, but overall it is fairly solid. So within NVMe, we are working on a key value command standard, and it will be a separate specification from the NVMe base specification. Right now within the committee, that piece of the standard is pretty close to done, but it relies on other work in NVMe to provide supporting structure for NVMe KV. It happens that that underlying structure is also necessary to facilitate zoned namespaces. So the structure that's under there is going to support both of those concepts, and there's two basic things that are being provided there. One is defining namespace types. So right now, everything is of one type, which is NVMe, or NVM. So the command set that's currently defined in NVMe base specification is the NVM command set, which in reality what that is the logical block command set. So this will support a logical block command set, i.e. the NVM command set, a zoned namespace type, and a key value namespace type. So that's namespace types, and within those, for each namespace, it is of a given type, and therefore it also only supports one command set. So I cannot have a single namespace that supports both a key value command set and a block command set. So I can't take for a particular namespace and send it a store command or a write command and expect it to operate on both of those. It will only operate on one command set. So the other piece of work that is the more complicated piece of work within the NVMe base specification is to separate out how do we deal with multiple command sets. And that's a matter of figuring out things that were written because they were for an I/O command set. They were written to be specific to the NVM command set. But a number of those things may actually need to be modified to say, well, these could apply to any I/O command set, whether that's logical block, zone namespace, or key value. So it's a matter of sorting out all of those things and getting them separated out so that we can talk about things that apply to a single namespace, a single command set, things that apply to multiple command sets that are not part of the administrative commands. The administrative commands in NVMe should remain the same. I see no reason that we will be changing any of the administrative commands with the exception of how you administer namespaces. So the expectation is to release for membership review sometime later this year all three of those things that I've talked about, which is the namespace types multiple command sets, the key value command set, and the zone namespace command set. I anticipate by the end of this year we should be moving into membership review on all of those. The namespace types multiple command set keys, I've touched on some of these already. One command set per namespace type. I already talked fairly much about that. The NVM command set is traditional block storage. The key value command set is currently being defined within the working group. So if you are an NVMe member, come participate. It's interesting work. And if you're not an NVMe member, come join NVMe. Zone namespace command set is also being defined within the NVMe working group. Same thing. If you're interested, come participate. So, features of the key value command set. Okay, this is where I get into some of the limitations that I mentioned early on. While we talk about a key being any length, being variable length, for the first pass at the KV command set, the key is limited to 16 bytes. Okay, this is a limitation that comes out of the standpoint that you have a certain command size that has been defined in NVMe. We could go to a larger size, but then all commands require that larger size. Doesn't sound like the place we want to go, at least for the first implementation. Most of the customers we've talked to are okay with a 16-byte key. So that fits within the existing command structure without impacting other aspects of that. So currently the key is limited to 16 bytes. Another thing, and this is actually an overarching, probably should have been up in the header stuff before we even got to the API. A key of 4 bytes cannot match a key of 8 bytes, even if the 8-byte key has padding. So what that means is, if I use this from a numeric point of view, and I have a key that is AD8790EF, that cannot match a key that is 0000, 0000, AD8790E Fox. Those two are different keys, even though they may numerically look the same, because they're of different length. Okay, so we're trying to make certain that people understand that you can't just take those two things and match them up and say, oh, but these are the same even though they're different lengths. Your key length is a part of what determines what the key really is. Okay, a key is of byte granularity. So you cannot have a 9-bit key. You have an 8-bit key, you have a 16-bit key. That is a limitation, and I don't see that changing anywhere as we go forward. Future work will extend the key length. There are a few alternatives that have been discussed, have a good idea of what direction we'll go with that, but that's future work that will be sometime next year.
One thing that's important to note is that you can mix and match key lengths.
Yes.
You don't have to have every key be the same length. You can have an 8-bit key coexisting with 16-bit keys, etc., and that's application defined.
Right, so thank you, David, very much. So basically, in a given namespace, you may have, you have variable length keys, which means that the length of the key is defined in the command. So I can do a store command of a 4-byte key value pair, and my next command do a store of a 6-byte key length key value pair, and so forth. When I retrieve things like the list, they're not necessarily going to be ordered by the length of the keys or any other structure. They could be. That's a vendor-specific implementation of how they store that information. So you may get a list that has a 4-byte key, a 6-byte key, an 8-byte key, another 4-byte key, and so forth in that list structure. So, and that is, there are characteristics of the namespace that the device can provide that can tell you what are your limits as to what you can do with this particular device. So you could actually do a device that is strictly a fixed size key. That's a valid implementation, but all of that information is information passed from the device to the host, allowing the host to then figure out how it wants to configure that particular namespace. So features of the key value command set, they are very comparable to what's in the API. I wonder why, since I helped to do both of them. Kind of had a little desire to make them look very similar to each other. So we have a store where you give it a key value pair, it stores that key value pair. You have a retrieve. You retrieve the key value pair based on the key that you give it. You have a delete, which deletes a single key value pair. One thing you'll note is missing on this particular slide. I don't have a delete of a group. That is not being defined in the first pass at the key value command set. You have a list, which follows all the rules that I've been over a couple of times in terms of the ordering of that list. You have exist. Exist in the initial implementation does a specific key exist in the device. It does not support the API version of doing a list of multiple keys. Now, the thing of note here is the API has something sitting behind it that is your driver for your particular device. That driver could actually do some of those enhanced functions in the host to then turn it into multiple exist commands or multiple list commands. That driver could actually do all of the work necessary to support key groups. So all of that can still be done using the existing API, using the first generation of NVMe KV command set. It's just that a piece of that work gets done in the host. So future work on NVMe. I think the number one thing that I'm getting pressure for is an extended key length. We have customers, we have all sorts of ideas on how big is big enough. 2K? I see some heads nod no. I see other heads nod yes. So what's big enough? Unknown at the moment, but bigger than 16 bytes, definitely. An append command. So right now, all of the store and retrieve operations are a single complete key value pair. We don't have a way to add data to an existing key value pair. The next thing here is retrieve index. We don't have a mechanism currently to retrieve a certain portion of a key value pair. You can only retrieve the entire thing. So those are a couple of items that have been requested and talked about for the future. They're not in the current command set. Key group support. As I said earlier, you can do key group support up in the host for the API purpose, but there's a strong desire to move that grouping function, the iterator function, the key group function, down into the storage device. So there's a desire to enhance the command set to support that key group function. I've heard at least one question here about sorting of your index. There is a desire to indicate whether or not a particular key value device is capable of providing your list in a sorted order. And if the device is capable of it, then we need to pass information about that capability and have some mechanism to indicate what type of sorting do I want of my keys. So sorted keys is something that we need to consider for future work. Exist multiple and delete multiple. Again, these are things that the API has already specified, can be done in the host, but eventually, as we have more capabilities on the device, moving those functions down to the device would be very useful. So applications for key value SSDs. They can run the gamut. What I've tried to do, I actually stole something from a Samsung presentation almost 3 years ago. So I don't want to go into a whole lot of detail, but my purpose of stealing this was to show the fact you have different applications that have different pieces of host code that are necessary to interface to the API, to your KV stack, and eventually to your key value device at the bottom. So when you get all the way over at just a NoSQL database, there's very little necessary from the API point of view. When you get over to a full object storage system, there's a lot more host interfacing that needs to be done to talk to the API, to talk to the key value storage. So it's a storage subsystem at the bottom that is designed to help facilitate other object storage or key value storage protocols, but not to be the end-all that does it all in the device. So software driver support. Samsung has provided source code, open source code that is available. Actually, this slide I missed. The first line on this, or second line on this slide that says currently proprietary needs to come out because it's no longer proprietary. We have provided at this link publicly available open source code that is written to the SNIA API. And there is both a key value SSD support as well as the NVMe user space driver. There is also, we have a Ceph object storage design specifically for our key value SSD that you can go pull down, look at how we have done a Ceph implementation. So there was something else I wanted to say in here, but just lost it. Okay, so that's the extent of the presentation. Last time I presented this, I found I had more questions than I had time for, so I tried having more time at this presentation to leave it open for more questions. So I will open it up to questions with the caveat that the questions stand between you and lunch. So I will not be held responsible. Yes?
Yes, so when you do a list, a command, does it list in logical block, physical block? What order?
So first off, we don't have logical blocks, which brought me to the other point I wanted to bring up. But we don't have logical blocks, so there's no logical block ordering. It is vendor implementation specific. And so what that means is a vendor may say, okay, I have a hash table that I store my key value pairs in. Whatever order that hash table happens to be in is how you get those key value pairs. There's no mechanism for the end user to have some idea of what the order would be. Yes? Yes? Thank you. So, yes, I'll repeat the question. The question was, have we looked at how to support key value drives over Fabric? One of the biggest things we looked at was specifically making certain that we were not using any NVMe commands that were not transportable across NVMe OF. So in particular, at one point in time, we were looking at using PRPs. There's some concern that PRPs are not supportable over Fabric, so we have avoided using PRPs and stuck to SGLs. So we have attempted to make this 100% Fabric transparent.
A couple of limit cases. Do you support zero-length key? I didn't say key. Can you have a 0-byte long key? Obviously, only one of them.
No. So the question was, can you support a 0-byte key, which would be only one key of 0 byte could be possible? And no, we don't support a key length of less than 1 byte. I don't think that, I don't believe we've really looked at that particular corner case. It's an interesting one. I don't know of a reason why we wouldn't support it. It's not difficult. I don't believe it would be. Okay, the question was, assuming someone wrote an application which wanted to use a logical block address as your key, and the size of your data was 4K bytes, and therefore implemented basically a logical block scheme on top of this, would it be slow, or do I have any estimates? My answer to that question is, I don't believe it will be slower. I have customers who have talked about things of that nature, so it's not something beyond the scope of what I see being done with this, and there's no reason in the world for it to be any different than a current logical block addressed system.
One last one. Do you have any, for that funny edge case, do you have any idea what kind of space overhead you're looking at in an implementation?
I don't see any space overhead above what's already there in the current flash translation layer. So the one thing that brought to mind, I want to make a point and then I'll come to your question. One of the things I didn't put down on future directions, it has been talked about whether or not we need to do some sort of data protection. And the question that has come up with that is, well, how do you define a data protection model for a variable length user data block of data? So that is something that we've left to theorize in the future, but a point, if you're thinking about logical block addressing and the fact that you have protection information potentially with it, we have kind of talked around that a little bit. So another question back there, yes.
Two questions. So first one, do I need to provide key length to each of the operations, like store, retrieve, etc.? That's the first one. And the second one is, are you looking to provide a native support in a programmatic languages such as Java or other to access the key value device?
Okay, so the two questions. First question, do you need to provide a length for the key in each and every command? The answer to that is yes, you need to provide a length of the key because you have to know how long the key is to know what you're storing. Because I can have two keys that look the same, but they're different lengths. So there is a length associated with each one. The second question was, are we looking to provide some sort of support for programming in Java or other languages of that nature? And we currently, from a Samsung point of view, are not looking at that. We're looking at predominantly providing the underlying support necessary for Linux.
So question about the data CRC side. So from the device, do you anticipate the CRC method got changed because of the error or the data allocated?
So that's where basically what I've said is we're not expecting to store a CRC with the data for the first release, and we have to determine what we do in the future. What I would anticipate doing is something along the lines of what SCSI did, of having a particular length of data that you associate some sort of protection information with the CRC, etc., and saying, okay, we will put a CRC with each n bytes of data, 4K, 8K, whatever it may be. But right now, we have no support for that at all.
Could you please repeat the difference between list and iterator? They're in the API, but
Okay.
not in the command section.
So the question was to repeat the difference between list and iterator. List is a matter of going down to the device and getting information about all the keys that happen to be on the device. Iterator is a process to go down to the device and say, I want to associate all the keys with this particular characteristic as part of a key group. So it's formatting, it is a command to tell the storage device, be prepared that if I query you with a request for a key group, that you're prepared, whatever preparation is necessary, which it may be time-consuming, that you've had a chance to prepare up front for commands related to that group.
This is for creating the group,
Correct.
but is that not based on some mask that matches the key? I thought it was based.
Thank you. So yes, it is based on a mask of the key, but depending on how you've stored it, if you've stored all your data in a hash table, it may not be easy to go get all the keys that match a particular mask in real time for a command. You don't want command timeout, so this allows you to prepare and say, oh, I've been told that I want to have a group that has this particular mask. Let me go find all the keys that match that mask and store them in a data structure that is easy for me to provide back the information related to that group.
You pre-build
Okay.
a list. You're pre-building a list.
Right. Okay. So just to let you know, I've got several questions. I'll try to get to as many as I can. I've already gotten the 5-minute warning. We'll start at the back over here.
Will exist operation be a constant time operation?
Say that one more time.
So will exist operation be a constant time operation, irrespective of the number of keys that are stored there on the device?
So I believe your question was, will the list operation... Will the exist operation be a fixed time operation? I don't know that anything can be truly fixed time. It is expected to be an operation that returns relatively quickly. So as quick as any other operation that you would, as quick as, say, a retrieve operation, or maybe even quicker than a retrieve operation. But I don't know that we have anything that is a fixed operation time.
No, what I want to know is, will it depend on the number of keys that are stored there on the device?
That's implementation specific. I have no idea. So, yes.
What is the granularity of the atomic rights in the key value?
The granularity of an atomic write is a key value pair.
Will
What do you mean by class of service?
Assume, let's say you have some NVRAM in the devices, will it be possible to utilize NVRAM separately than the underlying?
Again, implementation specific. So, yes.
Spec provide an interface to update multiple key value pairs.
One more time.
Does the spec provide an interface to update multiple key value pairs so that it can keep the transaction?
Okay. So no, the first level, that's part of where the first level spec, all it does is provide an interface to store a single key value pair in a single command. We don't even have an append command that allows you, which is kind of what I think you're talking about as an update, or I guess you're talking. Okay. Yeah, no, we're not looking at that at the moment. Okay, so I'd like to thank you all for coming. I have gotten the sign that we're out of time.